Hello, this is Byron Griggs, and this is my demonstration video for the final lab of simulation and concurrency. So going down this list in the Excel document, we have all three of the Newtonian physics are pretty easily visible here in the first scenario, scenario A. And then we've got collision between moving spheres and fixed spheres, also in scenario A. And you can see collisions between moving spheres and moving spheres here as well, and with the room. For the moving spheres and fixed capsules, we need to go to scenario B, and you can see the spheres bouncing around on these. And then inelastic collision response between moving spheres and fixed objects, including room. So we do have this collision response here. This is actually fully elastic. I'm not sure if this is a typo because, in my opinion, inelastic would be harder to model than elastic, but I do also have inelastic here. You can see these are almost completely inelastic. These are somewhat inelastic. And then we have between moving spheres and moving spheres of the same mass, as we can see here. And then scenarios. So scenario A here, we have one sphere spawns per second and a random location. And the fixed spheres are also random. They all have the same mass and radius. They do have random initial velocities though. Alright, for this second one we have scenario B, which has the same sphere logic, so spheres spawning one at a time for a total of 9 spheres, and we have these random capsules as well. And for scenario C we have mini spheres here. We have 500 total. And the simulation frequency here is actually quite good, but on my laptop it's limited by the render frequency, which, based on the profiler, I think is just my graphics card. And then this is mostly for the lab computers, the 2000 objects. We've also got scenario D, which is just scenario C but with some capsules as well. Again, 500 spheres. Well, 509 because there's 9 static ones. And we have custom scenarios, which we have for the advanced features. So here we've got these two spheres with different masses, and they have the same density. And then we've got these two spheres with the same radius but different densities. See, this one is much heavier. And then this is mostly inelastic. This is somewhat inelastic, so every time they collide they'll lose some energy. And then we've got this third one, which is 3 different objects that all have different elasticities. I do not have much to show for distributed architecture, so I'll just save it for the live demonstration. All I have is assigning colors and a UDP broadcast connection between 4 peers. I can't really talk about the threads without going into the code, but we can just skip to these frequency adjustments. So if we use scenario A, for example, or even scenario C, because it's more taxing on the computer, you can see the simulation frequency is adjustable, and on this computer it maxes out about 700 loops per second. And we'll reduce simulation frequency so you can see the time step. And perhaps it'd be easier to see on something like scenario A, so you can keep track of the objects. So yeah, you can see this time step here, and this should be a tenth of the distance moved for a given velocity. And in addition, we have our render frequency, and you can see that the render frequency is independent of the simulation speed. So that is some proof of threading. The network frequency is also adjustable. It won't do much even in the live demonstration, but on this computer it does pretty much nothing. And processor affinity would be in the code. For displaying the total number of objects in the simulation, you can see here spheres, capsules, and hollow cubes. Showed that earlier. Here's our target delta time. And we've got the simulation, render, and network frequencies for all of these. We've got a pause simulation here. We can show its behavior on a more taxing scenario. So you can see, actually turn this up. So you can see simulation frequency is at about 600. If we pause it, it jumps up to 1,000 though. We can toggle gravity here, cause them to spread out throughout the room. And we can also invert gravity. And we've got all these scenarios that we can change between. For the advanced Newtonian physics here, we have 3 different integration methods. And there is no discernible difference in the output because all of them are near perfect. So there's not much difference between them. But I mean, I did verify they're running with breakpoints. And they also don't really have any impact on performance. Objects don't have angular velocity. I don't have any cubes other than the box. No spatial segmentation. Spheres do have different masses, as I showed earlier, but we can show it briefly again. We do have elasticity, although in scenario A through D everything is perfectly elastic. We have no rotation. We do have a small amount of friction, but it's only used as a stabilization method to compensate for integration errors and floating point errors. I don't have any moving capsules or cylinders here, or moving cubes. I can show in the lab demonstration I have 4 piers, but they don't do very much. I do have a correction algorithm. Whenever an object is added into the scene, it adds it to an ideal momentum and ideal energy counter, so the sum of all the momentum and energy in the scene. In every simulation loop, we calculate the current momentum and energy in the scene, and based on the difference, we assign the friction value, global friction value, to -5% or +5% to increase or decrease the momentum. Things do get a little bit complicated with invert gravity and toggle gravity because you can actually increase the energy of a system if you were to say invert the gravity of an object while it's on the floor. So the ideal energy and momentum is recalculated every time you toggle or invert gravity. I don't have any robustness for packet loss. In the lab I can show I do have a UDP broadcast mechanism. I don't use compute shaders. I do have elasticity and friction, but they cannot be set at runtime. And I don't have explicit density, only implicit by changing the size and mass. So that's about it for the demonstration. Thank you for watching.